So welcome to this next lecture on sound and structural vibration. We have been looking at the structural acoustic waveguide. Last time we looked at this software called Maple. Let me show you what now the picture should look like. The rigid cut-on calculation didn't work out. Hopefully I'll show it to you sometime. So I will keep the uncoupled waves dotted and light. Okay, so that is the plane wave. This is my flexural wave. Now this is my first rigid duct cut-on. This is my second rigid duct cut-on. And so forth. Okay. Now we saw that the coupled plane wave was below here. Okay, a coupled plane wave was above here, and in this region it blew up. Okay, I told you that will happen. Okay, the reason is what? We did this expansion, xi is equal to omega plus a1 epsilon. Okay, so this was valid for this region and that region, not valid for that region. Okay, so that means this correction term should have some other form. I will tell you the form. It should have this form, plus a1 epsilon to the power half. That is why it did not work out. Okay. Now the flexural coupled wave, how did it look? The coupled flexural wave looked like this here. Okay, and below what happened? There was a point where it crossed, below it was lower, above it was higher. Okay. Now let me draw in some light color here. Maybe that is good. There are these points, or there are these light lines. What is that point? It is a critical point. What is that? Okay, let me draw these. So there are these lines now. So what essentially happens is my coupled wave starts here. Okay, it remains close to the plane wave. Here it transitions slowly into the flexural coupled wave continuously. Now I am onto the coupled flexural wave line, which crosses at a single point the uncoupled flexural wave, and then it goes beyond, and then it starts to follow the next rigid duct. I told you that these black lines can never cross the other dotted lines. Okay, because the there are three terms here in a product, and they have to be small enough to balance my epsilon. If they exactly go to 0 at any point, then there is no way to balance this. Okay, and therefore if I am on any one of these dotted lines, then I am exactly 0. If I am here, I am exactly on the acoustic plane wave, so second term will go to 0. If I am exactly here, I am on the uncoupled flexure, so first term will go to 0. So this entire term will go to 0, then epsilon will be left hanging. So no uncoupled line, no coupled line can exactly cross the uncoupled line, except there are exceptions. Okay, there are exceptions. Okay, and these are these exception points. So what happens to the rigid coupled curve, which I said did not work out? So it follows the rigid coupled line, uncoupled rigid line, comes up, becomes the coupled flexure again, so remains below, crosses the uncoupled flexure, goes above, and it starts to follow the next rigid uncoupled line, and this picture repeats. Okay, so if I have to again pick, let's say, blue, this is the coupled acoustic plane wave, this is the acoustic coupled plane wave, this is the coupled flexure, this is the coupled flexure, this is the coupled flexure, this is the coupled rigid duct cut on first fellow, and this is the coupled rigid duct cut on second fellow, and so forth. Okay. Now the naming is also appropriate if a coupled line is close to an uncoupled line. Okay, we'll call it the appropriate coupled line. So this black line is close to flexure, so we'll call it coupled flexure. So we'll call it one is uncoupled flexure, the other is coupled flexure. Okay, so that's the picture. Now let us look at a physical explanation. Okay, we'll look at the physical explanation. Of why this happens. That means why the coupled flexure here is above, why the coupled plane wave here is above, why the coupled plane wave here is below, and so forth. We will see the physical explanation for that. Okay. So in order to do that, let us look at the original equation. I have E I k x to the power 4th minus m omega square is equal to minus omega square rho by ky into cot kya. We will give this a number 1. Okay. Now we will say EI is the structural stiffness, okay, and m omega square is the structural inertia. Okay. Now please note that cot kya, because it is composed of cosine and sine, it will switch signs. It will have positive regions and negative regions in frequency. Okay. So it has a minus here. Okay. So let us say this entire term including the minus, entire term including the minus. Okay. If that term, we will call it fluid loading term. Okay. If the fluid loading term that means along with the sign, okay, is positive, okay, then it comes to the left side. When it is transferred to the left side, it becomes negative, and it adds where? It adds to inertia. It adds to structural inertia. That means the fluid behaves as inertia. Okay. So, the structure sees it as inertial loading, whereas if the entire fluid loading term along with the sign is negative, okay, then it adds to the structural stiffness. Structural stiffness. Okay. So whether Ky is real or imaginary doesn't matter. Okay, now we will see what that means. Okay. So we will try to explain, okay, we will try to explain the coupled flexure. Try to explain the coupled flexure. Okay. So what is Ky? What Ky is equal to square root of k square minus kx square, okay, and it is part of the equation 1. It's part of equation 1. So let us say we are looking below coincidence. We are looking below coincidence or below omega c, or omega below omega equal to 1. Omega is less than 1. Okay, and kx is approximately near kb, the flexure, or we will call it kp. Okay, we will call it kp. Okay, I forget what I have been using, kb, I think I have been using kb, so let us stick with kb. Okay, and therefore ky also will have square root of k square minus kb square. Okay, and because kx is close to kb, the relationship between k and kb also holds. Okay, so below coincidence k happens to be below kb, okay, and therefore k of y is imaginary. K of y is imaginary. Okay, so now what happens? We have, if we look at the non-dimensional form, of the fluid loading term, which is just minus epsilon cot kya by kya, okay, that term turns out, let me write it once more, minus epsilon cot square root of k square minus kb square into a by square root of k square minus kb square into a. So this term ends up looking like plus epsilon cot hyperbolic, okay, square root of kb square minus k square into a divided by square root of kb square minus k square into a. So note that I have switched k and kb positions, okay, and this is a positive term, this is a positive term. So this entire term along with the sign is a positive term on the right, okay. So what will that do? If it's positive on the right, it's negative on the left, that means it is an inertial loading. It is an inertial loading. It's an inertial loading, okay. And so what it does is actually slows down the uncoupled flexure, what I mean is as an inertial influence on the flexure and slows down the coupled flexure. That means the coupled lambda x is smaller. Remember, lambda x is distance covered in one cycle. So if it's slower, lambda x is smaller, and therefore kx happens to be bigger, and so kx becomes bigger than kb. Okay, so the structure perceives the fluid as inertia. Okay, and now since kx is a modification to kb, we'll call it coupled flexure. Okay, that's the nomenclature, coupled flexure. Okay, there is the influence of both structure and fluid, but because kx is close to kb, we'll call it coupled flexure. Now, what about beyond coincidence? Okay, beyond coincidence. That means omega greater than 1. Okay, here again I am looking for kx close to kb, but kb is less than k. Okay, and therefore you can see in equation, in the original equation, which is ei kx fourth minus m omega square is equal to minus omega square rho by ky cot, I'll open this, square root of k square minus kb square a. Kb is less than k already. Okay, so here also it's the same term, square root of k square minus kb square. Okay, kb is less than k. So therefore the cot term will change signs. Okay, the cot term will change signs. So how does it do that? So for 0 less than k by a less than pi by 2, okay, the correction, the fluid loading term along with the sign is negative. Okay. Hence what happens when it's transferred to the left hand side, it's positive. Okay. On the left it is positive. And therefore it adds as stiffness. Okay. Then this is important, there is one point, where cot goes to 0, cot kya goes to 0, and then beyond, okay, the fluid loading term switches sign, and becomes positive. Okay, along with the sign it's positive, which means on the left it is negative. Okay, and therefore it behaves as inertia. Okay, so then what happens? So if we look at that picture in the localized picture here, okay, my my original flexure is moving like this, okay, and somewhere I am beyond coincidence, and somewhere, okay, the cot ky is 0, beyond it is positive, and therefore it becomes inertial, before it's negative, so it becomes stiffness. So this is now my coupled flexure beyond coincidence. Okay, so there is this one point which is where cot ky goes to 0, it's a critical point. I told you earlier that coupled and uncoupled curves cannot cross, but this is one exceptional point where this crossing occurs. That means the coupled and uncoupled are equal. That means what? The correction is 0. That means what? The correction is 0. So even by the language, what that means is that the structure or plate does not see the fluid, does not see or experience the fluid. Okay, or the fluid pressure on the plate is 0. And hence the coupled wave behaves like the uncoupled wave. Okay. Now we look at that critical point, that's okay. We look at what happens at that critical point in a few minutes. Okay, but before that, this whole term which is minus cot kya by kya, okay, which is part of the correction term or main contributor, okay, is how does it behave in frequency. Okay, how does it behave in frequency? So this is my, I am going to plot it with respect to non-dimensional frequency. So this is omega equal to 1, okay, then omega equal to 2, then omega equal to 3, okay, omega equal to 4, this is omega axis. Below omega, so let us a 0 value, let us say this is a 0 value, okay, we plot it in red. So below omega 1, this term is totally positive. We have shown you that it is a hyperbolic chord, so it behaves like this, okay. So it makes it inertial, so this region is mass, the fluid loads the structure as a mass, okay. But just beyond, it starts to behave as stiffness, okay, becomes very light, okay, somewhere here there is a crossover, and at value of pi, okay, omega equal to pi, this thing blows up, and this region is mass loading again. And this region is stiffness. Okay, and this repeats now. So somewhere here again there is a stiffness part, it becomes light loading, crosses over, and again at 2 pi it starts to blow up. So this is reflected in the correction of the flexural coupled wave, okay. The time is running out, so I will explain to you why this crossover point is there and what happens here in the next class. Okay, we will stop here. Thank you.